today we're going to talk about the extreme value theorem. All right, we did this a little bit yesterday. So here's what the proof, all right, or here's the theorem. If f of x is continuous on a closed interval a to b, then f attains an absolute max f of c at c and an absolute minimum f of d at d, where we see f of c as a y value and f of d as a y value. Everybody, we got to go through this and see this, so I'm going to make a whole bunch of graphs about this theorem. Remember, if it's closed interval, those 2 points exist, right? F of A and F of B exist. Would you like to have some simple functions first? Then we have a parabola, right? In this case, the absolute minimum is D. That is F of D at D, right? There it is, right? That's the absolute minimum. Where's the absolute maximum? Well, this time the absolute maximum is B. B and C are the same. And this is F of C. Now, I can put this somewhere else, right? You notice this is continuous on a closed interval. And I can move this around. And I can make it at a different spot. Right? And then here's F of C. And now C is not on B anymore. C is right there, right? And again, not a surprise, it could be the endpoints or it could be the points in the middle. One thing we notice about this continuous function, right, is when I look at the derivative of those 2 points, this time they're 0. Now, can I get an absolute max or absolute min of a continuous function without it being 0? I can. So if I just get rid of the red curve, okay, and we'll leave the max and min in the same spot. Now, I just want to have us think about these things, all right? Because I can draw a bunch of these curves. How about this? All right. I think that I have not changed the absolute max or absolute min this time, but I do not think f prime of D or f prime of C exists in this graph. Because, again, a derivative is a limit. Obviously, the left and right hands are not the same at D. The green lines are not the same slope. And again, if I look up at points at C here, again, the left hand and right hand aren't the same. Again, we know that functions like this are not differentiable. Does the extreme value theorem hold true still? Absolutely. Is this a continuous function? Absolutely. So it has a min and a max, an absolute min and max. All right. So we know this always happens, but we got to be clear. This theorem you got to make sure it has some caveats in that I don't have to have just one. You guys picture kind of a trig function? All right. You can see that there's an absolute max right here, right? And that would happen at C, is what we've been calling it, and this would be f of C. That is the absolute max of this function. But I want to be clear, this has 2 absolute mins this time. So maybe I call it D1 and D2. What's the value of both of these? F of D. I would do F of D asterisk down here because the asterisk gets replaced with the 1 and 2. But that absolute minimum, if I ask you for the absolute minimum, it's still a single statement. If this was, 5 and 3, the absolute minimum is 3, happening at D1 and D2. The absolute maximum is 5, happening at C. All right? Now, someone's got to be thinking, is there a way that this doesn't work, where it's a continuous function? We're going to show some ways it doesn't work with, when it's not a closed interval or non-continuous. We'll show why it doesn't work for those. But is there a way this fails? Well, it says f of x, it's got to be a function. Well, this is always confusing for students. Let's start. Yeah, the absolute max and absolute min is every point. So here it is. Let's call it a value of 5. Let's have the function y equals 5. Guys, the absolute max is 5. The absolute min is 5. Happens everywhere. F of x equals 5. Yep. So everybody, the min and max are 5. So in this case, the theorem works. There's just 1,000, a zillion, there's an infinite number of c's and an infinite number of d's. And f of c and f of d are both the same, and it's the absolute max and the absolute min. This is a stupid problem to do. Do you agree? We don't do problems like this, but I want to make you sure that this is how it exists. What really gets students is it has to be continuous. All right? And when it's not continuous, all kinds of bad stuff happens. Because if, my favorite thing is have a solid point, and put it in an asymptote. Guys, this has no max or min, right? But it's not continuous. All right? Likewise, it has to be a closed interval, and I think we did some of this, a little idea on this yesterday. This has no max and min because it's open. So those conditions are extremely important. It comes down to, as long as you have a closed interval, you have a max and min. You need to check the endpoints and all the fun points in between, right? So the question is, how do we define the fun points? So I'm going to move ahead, because this brings us to the next idea. Fermat's theorem, all right? If a function has a max or min at c, and f prime of c exists, then it has to be 0. All right. This is important again. I don't even need, I just have c and f of c. I'll put that point. If I draw a max in, there's a local max, right? Does the derivative exist? Yeah. Guess what? It's 0. If I take it away, min, 0. Now the problem is does f prime of c exist here? In this case, f prime of c for the graph I just drew, DNE does not exist. All right? Is it still a local max? Yes. All right? The big thing that confuses students here is this is a one-way street. If it's a max or min and the derivative exists, it's 0. If the derivative is 0, is it a max and min every time? No. In fact, we're going to do a couple cases right now to prove this, because we want to make sure we see this as a one-way street. It is a one-way street. Max min f prime exists means f prime equals of c equals 0. It is a one-way street. All right? It does not go backwards, okay? And I can show you on one of my favorite graphs. All right? Not vice versa. All right? Not vice versa. Okay? And to show you that, can we picture in our heads one of our great parent functions x cubed? Oh, yeah. What's the derivative of x cubed? 3x squared. The power comes down, you reduce it by 1. Guys, where is f prime of c equals 0? What value of c? 0. Look at 0. Is it a max or min? No. Is it a local max or min? No. Now, you can kind of see something interesting is happening here. Kind of see how it shapes, it's changed its shape, right? We'll get to that later, all right? But just because the derivative is 0 at 0 did not make this a local max or min. It does not. All right? Likewise, just because it's a max or min doesn't mean there's a derivative. This is the case of, listen, the derivative was 0 and the point was nothing. The other option that gets students confused, let's go to my other favorite function that's continuous. Absolute value of x. Is there a minimum on this one? An absolute minimum. It's 0 at 0, right? We can tell by the graph. Does the derivative exist at 0? No, it does not. Guys, here's the thing. The funny part about this is, if I want to find the derivative, I tell you it doesn't exist at 0. What's the derivative to the right of 0? 1. Why is it 1, Skylar? Up 1 over 1, up 1 over 1, up 1 over 1, right? This is absolute value of x. On the positive side, it's just y equals x. Guys, what's the slope on the other side? Negative 1. This is a great derivative, right? Think about it. This is our understanding of it. But I come back to, let's be clear, does it have a minimum? You bet. Is the derivative at the minimum 0 on this graph? No. But if you know it's a max or min and you know it has a derivative, guess what? If then you can say it's 0. All right? Polynomials, this works well, right? If we think about it. And we know they're continuous. We know they don't have little points or birds, all right? All right, so we've done all this work to lead us to one giant thing. All right? We've done all this to lead us to one idea. So, if f prime of c is 0, it's still important, right? It's so important. It's still important. It's a critical number for us. Critical, c is critical. In fact, so critical we call it a critical point. So every time we get a derivative now, we're going to be interested where that derivative equals 0, because there's a chance, right, that's either going to be a maximum or a minimum. All right, so we're going to cut the lecture there. We're going to do problems in a separate video. Check for the next one.